Hi techies! Quantum computing, journey from bits to qubits, takes you on a fascinating exploration of the next frontier in computation. From the familiar world of classical bits, zeros and ones, to the mysterious realm of qubits, where information exists in superposition and entanglement. This journey reveals how quantum mechanics is redefining the limits of technology. While breakthroughs continue to push boundaries, the road ahead is still long and full of challenges. Join me as we uncover how far we have come and how much further we have to go in realizing the true potential of quantum computing. Join me in this journey of the future now, where we explore the technologies that are transforming the present and defining the future of tech. Watch this entire video and let's get started. Quantum computing, journey from bits to qubits, still has far to go. Introduction. The next generation of computers could redefine science, security, and global power, not through bits but through qubits. In 1981, physicist Richard Feynman issued a bold challenge. If the universe runs on the strange rules of quantum mechanics, why are we using classical computers to understand it? His idea that a quantum world should be simulated by a quantum machine sparked one of the most revolutionary pursuits in technology. For decades, computing advanced from mechanical calculators to digital systems built on bits, tiny switches representing zeros and ones. This digital revolution transformed every field from science to communications. But as researchers tried to simulate the complex behavior of atoms and molecules, they reached a fundamental limit. Even the most powerful supercomputers failed to capture the intricacies of quantum phenomena, where particles can exist in multiple states at once and influence each other rapidly across vast distances. That's where quantum computing comes in. Unlike classical bits, qubits can exist in a superposition of states and become entangled, enabling them to process information in ways no traditional machine can. These strange quantum effects aren't just scientific curiosities, they hold the key to solving problems once thought impossible. From designing new materials to breaking encryptions and advancing artificial intelligence, Feynman's vision endures to build a machine that doesn't just calculate faster but compute in harmony with the very fabric of nature itself. Harnessing superposition and entanglement. The Heisenberg uncertainty principle, part of the bedrock of quantum mechanics, tells us that certain pairs of properties, such as position and momentum, cannot both be known exactly at the same time. This fuzziness gives rise to superposition, where a quantum system exists in a blend of states simultaneously. For a qubit, superposition means it can be 0 or 1 at once, like a spinning coin, undecided until it lands. Only upon measurement does its state collapse into either 0 or 1, enabling parallel exploration of possibilities. Even more astonishing is entanglement, a uniquely quantum link between qubits. When qubits become entangled, their individual states have no independent meaning. You can only describe the system as a whole. Measuring one qubit instantly determines its partner's state, no matter the distance between them. A phenomena Albert Einstein dubbed spooky action at a distance. How to tame a qubit? The main challenge is to harness quantum states for computing, as they are extremely fragile. Tiny disturbances like thermal vibrations, stray fields, or cosmic rays can destroy superpositions through decoherence. Today's qubits stay coherent for only 10 to the power minus 5 to 10 to the power minus 4 seconds before error appears, whereas classical memory can preserve data for milliseconds to years. To counter decoherence, researchers cool qubits to near absolute zero, isolate them in a vacuum, and apply error correction methods that combine many physical qubits into one robust logical qubit. These logical qubits detect and correct small errors in real time, protecting quantum information long enough for useful computation. Despite the difficulties, key milestones have been achieved. In 2019, Google's Sycamore processor completed a special sampling task in 200 seconds, estimated to take 10,000 years on a classical supercomputer, demonstrating quantum advantage, even though the problem had no direct practical use. Since then, IBM has built systems with over 100 qubits and is aiming for 1,000. China's Zhejiang phonetic quantum computer has shown similar advantage using light, and startups like IonQ and PSI Quantum are pursuing scalable alternative qubit designs. Quantum promise and peril. If successfully developed, quantum computers could transform industries across the board. In pharmaceuticals and materials science, they could revolutionize molecular design by simulating chemical reactions and protein folding with atomic precision, paving the way for faster drug discovery and novel materials. In logistics, transportation, and finance, quantum optimization algorithms could deliver vastly improved solutions for traffic management, supply chain efficiency, and portfolio risk balancing. In the field of cybersecurity, quantum communication promises virtually unhackable networks through quantum key distribution, a technology already being tested in several countries. They could also threaten today's security. Shorts, quantum algorithm can factor large numbers exponentially faster than classical methods, putting public key systems like RSA, ECC that secure internet banking, e-commerce, and government communications at risk. When large error-corrected quantum computers arrive, they could decrypt decades of digital traffic overnight. This has spurred a global push towards post-quantum cryptography, new codes believed safe even against quantum attacks. Effective storage today. A nominal 100 qubit system can, in theory, represent 2 to the power 100, which is equal to 1 into 10 to the power 30 states simultaneously, requiring some 10 to the power 31 numbers to emulate on a classical machine. Yet, with current error rates and no full error correction, those 100 physical qubits effectively yield fewer than 5 fully reliable logical qubits, enough to hold only 2 to the power 5, which is equal to 32 basic systems or states in superposition. By contrast, a typical laptop's 1 terabyte drive stores about 8 into 10 to the power 12 classical bits reliable for years. Today's devices host tens to few hundred qubits but suffer from limited coherence and high error rates. So only small scale algorithm demonstrations are possible. Global race for quantum computing. The total public and private investment in quantum technologies has surpassed $55 billion over the last decade. China leads with over 15 billion USD in public spending, and the US follows with about 4 billion USD. And the European Union with 1 billion euro quantum flagship rounds out the top 3. Each nation seeks both technologically leadership and safeguards against quantum enabled threats. In India, the 2020 National Quantum Mission committed 8,000 crores, that is 1 billion USD over 5 years. Research groups at the IITs, IIScs, and TIFR, along with several startups, operate 5 to 10 qubit systems today and aim for 50 to 100 qubits by 2030, enough to begin tackling more complex problems and cement India's role in the quantum ecosystem. India's initial funding injection places it among the top 5 investors alongside the UK, Canada, and Japan. Looking ahead, a fully fault-tolerant quantum computer with millions of physical qubits supporting error-corrected logical qubits remains years or decades away. Yet, the work today in improving qubit stability, scaling control electronics, and rolling out quantum-safe encryption lays the groundwork. Quantum machines will not replace classical computers but will augment them, tackling specialized problems, the computational toughest subroutines like simulating quantum materials, solving large-scale optimization problems, and breaking cryptographic codes that classical systems struggle with. As this new paradigm matures, we stand on the brink of an era defined not by what's possible with bits, but by what can achieve with qubits. I hope you enjoyed this video and gained valuable insights into the latest tech innovations. The future is now and the possibilities are endless. Stay tuned for more exciting deep dives at profound insights under the Future Now, the latest in tech playlist. If you like this video, please remember to click the like button, subscribe for more exciting tech updates, and share your thoughts in the comments below. Your engagement motivates me to create more content like this. Until next time, stay curious and keep innovating. Thank you.